Hello and welcome back. So in previous episodes, we talked about the half adder and the full adder, and we used the full adder and half adder to construct a 4-bit adder that adds 4-bit numbers to 4-bit numbers. So today we'll be talking more about the engineering side of things instead of the theoretical side of things. So in engineering, efficiency is oftentimes very important, and we can sometimes express efficiency through its time efficiency, its space efficiency, and its overall complexity. To tackle complexity, it's often easier to use less numbers of different logic gates to in our logic circuit construction than to use a lot of different gates using not, and, or, and everything else. So to reduce complexity, we need something called functional completeness. So a set of functions, a set of logic operators are called functional complete if they can be used to construct every formula in the propositional logic. So a well-established set of functional complete operators is the set of and, or, not, the single-sided conditional, and the biconditional. And we know that we can construct the biconditional simply by using two conditionals, and an and. And we know that we can construct a conditional using just not. Sorry, sometimes they use this for not, for simplicity, not A or B. And at the same time, we know that by De Morgan's law, we can construct and using a not gate and an or gate. And we can use an or, we can construct an or using only the not gate and the and gate. So we see here, we only need the not and the or the not and the and to be able to construct everything we see here. Every gate not and XOR conditional, biconditional, and everything else. And a few hundred years ago, a few scientists realized, hey, the NAND gate and the NOR gate can be used to construct are themselves functional complete. So we'll illustrate this by using only the NAND gate to construct the NOT gate and the AND gate, which we've seen previously is functional complete. Let's move on to logic.ly. So let's start off with the NOT gate. So NOT takes in one input and gives one output. Let's link those up. So we can see that it's zero, it's one when the input is zero, and it's zero when the input is one. So how can we do this with the NAND gate? In fact, it's quite simple. If you just pass in the input to both inputs for the NAND gate, you will construct a output that is equivalent to that of NOT. Because the NAND gate is one when either input is zero, sorry. And it's only zero when both inputs are one. So if we toggle this on, wait a minute, sorry. If we toggle this on, we can see that both inputs to the NAND gate are one, and we result in a result of one, result of zero, which is the same as the NOT gate. So let's move on and let's try to construct the AND gate. So the AND takes in two inputs, pass it through the NAND AND gate, and we should get one result. So let's build that first. Let's put it here instead. And this should be the same, and we should only be using the NAND gate. So we know that the NAND is simply a negation of AND. And as we've seen in the previous example, we can easily construct a negation using a NAND gate. So what we do is we pass in both inputs to the NAND gate, and this should give us the exact opposite of the result we should be given to an AND gate. And what we need to do next is simply negate it using the same technique we used before to construct the NOT gate. That is not what I wanted to do. Let me take that out. And by testing this, by switching them on and off, we can see that they are equivalent. Their results are always the same. It just keeps popping out, sorry. But I hope you get the idea. So as seen here, we can use simply the NAND gate to construct the NOT gate and the NAND gate to construct the AND gate, which means that the NAND gate itself is functionally complete. And you can do this with the NOR gate also. I encourage you to try doing that. And this is a full table of constructing every logic gate we've seen so far using the NAND gate. But something you might notice is that looking at the last 3 rows, you can see that we're using a whole lot of NAND gates to construct a single logical operator. And you might think to yourself, how is that efficient? Well, that kind of boils down to the physical implementations of these gates. So as we said before, efficiency is space efficiency, time efficiency, and complexity. And we've already talked about how having one kind of logical operator is a lot less complex than having all of these different operators, right? Okay, now about space and time. In fact, the fastest operators we've seen that takes in 2 inputs are the AND, the NAND, the OR, and the NOR. So these achieve the highest time efficiency, and they have the least delay. And we know that the AND and OR are not functional complete, so they have a higher complexity, so we're not going to use them. And speaking of space efficiency, just simply based on the physical implementation of the NAND gate and NOR gate, the NAND gate is physically smaller than a NOR gate. So the NAND gate achieves the highest space efficiency. So this would mean that the NAND gate would be the most efficient and effective choice in an engineering solution. And it would be the most cost efficient at the same time. Now, I would encourage you to try to construct a full adder and a half adder using only the NAND gate. And as an exercise, it's going to be difficult, but I believe that you can figure it out. Good luck. And let me know if you have any questions.